Good afternoon, ladies and gentlemen. We've got 20 minutes to tell you all about the quantum computing. We've been in the binary computing area for the last 6 years, but we do have quantum technologies in a small way inside our computing systems now, but they're going to go big time, and these guys are going to explain how. First we've got Serguei Beloussov, who's the CEO of Acronis, who I'm sure you all know, but he's here today in other capacities, which I actually have to read out for you. He's the co-founder of a fund, QF Capital. He's the chairman of the board of trustees of the Russian Quantum Center, and he's a member of the governing board of the Singapore Center for Quantum Technologies. We also have Tommaso Calarco, who has the excellent title of Director of the Center for Integrated Quantum Science and Technology at the University of Ulm, Stuttgart. But he wants you to know him as the man the EU has given €1 billion to research quantum. Sergei, over to you.
All right. Hi, everybody. I will give a first introduction into why quantum technologies are important. It's typically very difficult to explain what is quantum technology, and it's still difficult even though quantum mechanics is 100 years old. And so before Tommaso will try to explain it to you so that you will understand why you make an effort, I wanted to talk why. And so actually, I was just thinking when I was preparing for the speech that everything new is forgotten old. And there is this wonderful place, Sistine Chapel in Vatican. Any of you have been to Sistine Chapel? Right, it's amazing, right? And Michelangelo is an amazing innovator of his time. And he has created the Sistine Chapel. There is a lot of details in the chapel. But there is one particular picture of a Judgment Day, which is on this slide, which actually has an explanation of why quantum technologies are important. The first part is about the fact that in the modern digital world of classical data, there is no longer privacy. There is no longer security. Everything about what you do can be known today, and in the future, when you have sensors all over you, when you have cameras everywhere, when you do every process in digital way, there is no way to ensure privacy. Everything you've done wrong can be known to somebody else, and that's why you're going to be sent to quantum hell. And the only one way to ensure security is a quantum security. It's security based on the laws of quantum mechanics, which can actually guarantee privacy and security of communications, can guarantee randomness of the key, can guarantee ability to control remote devices. And there are real companies which are already deploying quantum networks, like ID Quantique. This is a company where I'm a chairman of the board. It's actually Swiss company, and they're deploying quantum networks in China, in Korea, in US. So it's already working devices. Those are the only devices which ensure privacy. And of course, there is also a heaven, which is described on this picture. Heaven is amazing. And what you can do with quantum computers is also quite amazing. For example, you can make amazing new materials, such as materials described here, like high-temperature superconductors, which can enable you to have flying cars, or enable you to have ultra-fast magnetic guns, or it can make very, very strong materials, like 100 times stronger steel. Think about why is it important to have 100 times stronger steel? Well, very simple. 100 times stronger means 100 times lighter. Think about you driving a car. Modern car is about 2 tons. Well, with new material, which is quantum steel, you can make a car which weighs 20 kilos. So you can literally put it on the top of your garage with your bare hands. It sounds freaky, but it's totally possible. In order to do this, you need to have quantum computers to simulate materials. And more importantly, quantum computers can solve some very difficult problems, like factorization of numbers or search very well. There is also a lot which indicates that quantum computers could be incremental for artificial intelligence. And so, there is a possibility that IBM Watson will run for president in the United States. It's possibly better than Hillary Clinton and Donald Trump. And in the future, it's definitely a possibility. And that's why quantum computers are very actively researched by companies like Microsoft, Google, IBM, Alibaba, Huawei. And there are real devices which are already able to perform quantum calculations, which are in work today, such as this quantum computer from D-Wave, which is a Canadian company. Okay, at this note, I pass it to Tommaso, who will explain to you what is quantum technology.
Thank you. So I have a couple of slides which show you the different applications of quantum technology. And the first one is, well, the main point is that computers are already physical devices, which already, what you have in your pocket, your cell phone, is already a quantum device. Without quantum mechanics, it would be impossible to produce transistors, lasers. We wouldn't have Facebook. We wouldn't have, the internet. But this is the old quantum revolution, the first quantum revolution, based on understanding the properties of quantum mechanics in last century. What is coming now is the second quantum revolution. So the point here is that we are able to exploit individual quantum systems like single atoms, single electrons, single photons. And they have properties which are completely different than the properties that we know from normal information processing. One example is, for instance, entanglement, which is, entanglement is the correlation between different, OK, let's forget it. Entanglement is the correlation between different particles at a distance, which can be used for secure communications. I will show that in the next slide. So the thing that I want to show in this slide, I have 3 slides now. One is about quantum simulation, one about quantum communication, and one about quantum sensing and metrology. And I want to tell you, in short, how those applications can impact our daily life. Yeah. So the point about simulating materials was made by Sergei before. And here the point is, well, this is a view graph that is very dear to me, because it is the only scientific view graph that I showed personally to 2 vice presidents of the European Commission, and they asked questions about that, okay? And the reason is it is not very technical. It looks technical, but the point is you have heard about quantum computers, and people say, oh, they are developing them since 15 years, but has it really come? I mean, we have yet to see it. It looks a little bit like cold fusion, and will it ever come? And here it comes. So what we have here is a black line, is the biggest supercomputer in Europe, which is occupying an entire building, okay, of computers and cooling and so on and so forth, and it requires a lot of electric power, and it is calculating some properties of a magnetic material here. And after some time, it stops because computing power is over. And then there is the quantum device, which is fitting on a table that big, the size of your dinner table. It requires the electric power which you have in your home. And what it does is it computes the same thing, and then it goes a little bit beyond. And I say a little bit, there is a few oscillations here. This is not yet a full-fledged, it is a prototype, but which is why I say first hint, but this is already going beyond what the biggest supercomputer in Europe can do on something on the size of your dinner table for computing properties of materials. One example is high-temperature superconductors, as Sergei was mentioning, that can be developed and understood only via these machines. So another example is quantum communication. So I mentioned before entanglement. At a distance, you can have, for instance, teleportation of quantum states between photons. It has been realized already 20 years ago. And this is already commercial. So there is a company which Sergei mentioned, which is ID Quantique, which is also contributing to funding. And you can buy these devices. So you put this box in your server rack, and via optical fibers, you get secure communication. Why is it secure? Because the first quantum revolution is I am sending over optical fibers a lot of thousands, millions of photons, okay, per bit. Now the NSA wants to hear what I'm saying. What they will do is they take, let's say, 1,000 photons. Now, with quantum communications, single photons, it cannot be broken, it cannot be split. So if they take it, we will immediately notice, and if the communication is received, we know for sure that it is secure. And this is something which is already commercially available. And now my last point here about metrology and sensing, which is essentially you use, again, these individual quantum systems, either to measure time, which is essential for GPS navigation. Today, for instance, you have, when you sit in your car, you have like meter resolution, every few meters the position gets updated. With this, it could go down to centimeters or even millimeters, which is essential for autonomous driving. And also, you can use this individual quantum system to measure other things, like measure, for instance, you can, with this nanodiamonds, you can measure individual activity of neuron cells. You can map your brain in real time. And so all of this is a range of applications for quantum technologies. Of course, I had only a few minutes to describe that, which is showing you the breadth of the possible applications that will impact our life in the future. And that's it.
Thank you, Tommaso. My first question to both of you, it's no longer a science problem, it's an engineering problem, right? And what is that problem? Is it just getting the processing power to bear on quantum computing?
It's about putting many of these individual atoms and photons together, work in a quantum way. This is the problem in quantum computing and in quantum simulation. Is the problem of scaling the distance of transmitting those single photons. You need quantum repeaters for that. They are secure because you cannot copy information in quantum world, so you need to have a little quantum processor that does teleportation over longer scales up to the satellite dimension. It's about making things bigger and working efficiently as well as reducing costs. So this is something for which you have to take it out of the hands of physicists and give it to engineers so that they can develop real devices.
So let me answer it a little bit differently. So transistor was invented in the 50s, but the science which enables invention of a transistor was invented many years before, 40 years before. Now, for invention of a transistor, people got Nobel Prize. So even though it's an engineering problem, it's a scientific engineering problem. The main problem is that quantum states are very fragile. And you need to build a very complex quantum state from many quantum bits. And that is very difficult to do in a sustainable manner. And the scientists are studying different ways to make it in a sustainable fashion and in a large scale.
Okay, now this is the RISE conference, and people in the audience are thinking, look, I love the idea of transforming the essential paradigm of computing, but how do you monetize it? So where can entrepreneurs and investors play in the quantum today?
Right, so no, there's multiple sense. So one of the sense which actually Tommaso started from the most complex and finished with the most simple sense is sensors. And it's amazing, but you can measure with the quantum sensors anything, electric field, magnetic field. You can make a sense which depend on measurement of electric fields and magnetic fields and gravitational fields, which are super precise. And sensors are very important for Internet of Things, for wearables, for autonomous devices like drones, like connected cars. And one thing, if you are doing something in this area and you need a better sensor, for example, you want to have a wearable device which can constantly monitor contents of your blood, you can find scientific groups who can potentially help you to design such sensor. Also, you can make sense which are exceptionally low power consumption. Again, quantum devices are the smallest and the most power efficient. And again, if you have a power consumption problem in your device, that is something which can potentially be solved with quantum sensors or quantum devices. And there's many other applications of quantum communications. One of them is related to very basic security. One of the reasons why the world is insecure, as we are told by Edward Snowden, is that we use random number generators, which are actually not random number generators. They're actually generating numbers which look random, but they're actually not random. They are actually, you'd think it's a 2-kilobit key, but in reality, it's actually 10-bit key or 100-bit key only. And with quantum random number generators, you can be guaranteed to generate random keys, which is important for security. It's just some examples.
Just to pick up on something you said there, quantum is very low powered, so the guys managing data centers today who are struggling with these big power bills, they're going to see a cut in their power bills in the quantum era.
I think it's actually a little bit different problem. I think the problem, the way it works, is that the modern IT is driven by Moore law, by the law which was invented by Gordon Moore about more than 50 years ago, that the computing power will go up every 1.5 years by 2 times, right? And this law is no longer working. And so for one thing, the IT industry is changing to a little bit different architecture to continue this growth. But the fact of the matter is there are problems which are very common to companies like Google and Baidu, to many companies, which are extremely power efficiently solved by our brain. So brain is a very funny device, but it's the most complex device in the world, and it is thousands of times more power efficient than computers in, for example, recognizing patterns. And on quantum computers, potentially you can make a pattern recognition of different patterns, which is thousands and millions of times more power efficient than on a normal computer.
That's actually the motivation for such companies as Google, IBM, Microsoft, Intel to be investing hundreds of millions on this in the US.
I'll just give you an example. I was recently going to a food court in Singapore, and I was talking to 3 people, and I was walking, and with the left side of my eye, I see there is some lady who is standing, and I see her back, and I see a part of her nose, and I think, I might know this lady, and I think, okay, that's the wife of one of my former employees. Well, this is a kind of pattern recognition which human brain can make. I mean, before that, I've seen this lady, say, 5 years ago. For any normal computer to make the same pattern recognition as I did in a split second without much power, it will be a huge cluster which will have to make a very complex manipulation and so on and so forth.
Right. Now, Tommaso, the EU has just given you a substantial grant to pursue research in quantum. What's their interest in quantum? What are they looking for?
So what they want is to not miss the train this time again of the innovation, because we have very strong scientific excellence in Europe, but the big investment from industry, the take-up, as I mentioned before, is taking place in the US and a lot in China. They are building a 2,000 kilometers quantum communication secure segment between Beijing and Shanghai. So the Commission wants really innovation and job creation and growth to happen in Europe. They want take-up from European industry. And they understand that to bridge the valley of death, this is the investment that is needed. On the other hand, we had people from the US at a conference that we organized 2 weeks ago in Amsterdam on these topics, telling me from the Office of Science and Technology Advisor of the President of the United States, telling me that they would like to learn from us in Europe how to make such a big, unified, organic program in their country. So what we can do in Europe is, in a united way, to bring industry take-up and growth on site somehow in our continent. This is the motivation by the Commission.
And what are the areas of research focus for you?
So there are essentially 4, which is quantum simulation, quantum computation, quantum communication, quantum metrology and sensing, as I mentioned before, plus all the development of software, algorithms, protocols, which we could call quantum apps.
Yeah. Look, so one of the really big capabilities of quantum, obviously, is security and essentially being unbreakable. Let's fast forward 20 years, we're in the quantum era, and let's say a government agency wants to crack into a device which is quantum secured. How does that scenario play out?
Well, first of all, today, security devices which are quantum, they are only guaranteeing the fact that nobody reads your communication from point A to point B. And that means that government still can force you to give the communication at point A or at point B, right? So in order for this to be fully secure, you need to have quantum computer communicating with quantum computer using quantum communication. And that is in the future. But generally, security is a very, very, very difficult space with a lot of secrets. You know, if you think about Egyptian society, in Egyptian society, there were pharaohs, but the society was very much controlled by the priests. And the priests, they had some special, secret knowledge about the world, which they would never disclose to the pharaohs, and they would never disclose to the public. And security is sort of this kind of field. So people don't really talk about it too much. Chinese listen to Americans, Americans listen to Chinese, Russians listen to Americans and Chinese. Everybody in the world is listening to each other. Nobody's talking about it. Of course, in the quantum world, it will be more difficult. But as I pointed out in this Judgment Day picture, really the invention, the creation of a functional, scalable quantum computer combined with quantum sensors, combined with quantum communication is going to change the world much more than what happened with traditional IT. And so it's hard to say what happens with the governments. Personally, I think governments is an outdated concept. It's better to have the world which has no governments and which has no borders It's quite stupid that people think that they are from Europe, or they are from United States, or they are from Russia. It's really funny concept that you have governments. But, of course, governments are still there.
Yeah, we're stuck with them. Okay, well, that's a good note to finish up on, Sergei. Thanks very much for that, Serguei Beloussov, Tomasso Calarco. Thank you, people.